There is a device that was once a standard fixture on rooftops across the United States and Australia. No motor, no electronics, no electricity. Independent testing showed it could reduce peak attic temperatures by as much as 37 degrees Fahrenheit and cut cooling costs by nearly 15% for free every single day. Then it largely disappeared from American homes. And the reason it disappeared had nothing to do with the physics. The physics was never the problem. The problem was the device itself. And here is the part almost nobody knows. Engineers went back, identified every single flaw, and fixed them. What exists today is not the same device your grandfather had squeaking on his roof. It is something considerably better. The bearings do not fail, the materials do not corrode, and most homeowners have never heard of it, which means most homeowners are still overpaying on their cooling bills for a problem that was solved years ago. To understand why the upgrade matters, you have to understand exactly what went wrong with the original. The turbine ventilator, patented in 1910 by an engineer named Samuel Ewart, was a spinning cowl mounted at the roof ridge that used three compounding physical principles to pull hot air out of an attic without consuming a single watt of power. Bernoulli's principle caused pressure to drop as wind accelerated across the curved vanes, creating suction. The stack effect meant warm air rising naturally from below kept the system working even when the wind died down entirely. And the Venturi effect, as air squeezed through the narrow gaps between vanes, accelerated the exhaust cycle further. Three separate forces, all working together, all powered entirely by physics. The device had no fuel cost, no maintenance schedule, and no moving parts that required electricity to drive them. The performance data was compelling. A study conducted in the San Diego area found that a properly installed system reduced peak attic temperatures by up to 37 degrees Fahrenheit. Research by the Air Infiltration and Ventilation Center found that turbine ventilators increased attic ventilation rates by an average of 15% over a full year, with improvements of up to 50% when wind hit the unit from its optimal direction. According to the United States Department of Energy, every single degree of attic temperature reduction translates directly into a measurable reduction in cooling load, up to 4% per degree. At scale, that translated to average energy bill reductions of 14.6% with zero operating cost. For a device that cost between $20 and $100 in materials and required no electricity to run, the return on investment was difficult to argue with. The problem was never the data. The problem was the hardware delivering the results that data promised. But the original design had three critical weaknesses, and each one chipped away at its adoption until the device nearly vanished from the American roofline entirely. Here's the important part though, every single one of those weaknesses has since been engineered out of existence. The version available today is not a compromise. It is a direct response to every documented failure mode of the original. The first weakness was mechanical failure. The spinning head of the original turbine relied on standard steel ball bearings that degraded over time when exposed to moisture, dust, and temperature cycling. When they failed, the turbine produced a grinding or squeaking noise that transmitted directly through the roof structure and into the living space below. Cheap, imported units were especially prone to this, and the resulting reputation for noise and unreliability followed the entire category for decades. What engineers discovered was that the bearing itself was the problem, not the concept. Modern turbine ventilators now use permanently sealed, permanently lubricated bearings rated for the full life of the unit. Independent stress testing has verified units maintaining silent operation after exposure to sustained winds exceeding 110 miles per hour. The noise problem, the single most common complaint against the original design, no longer exists in quality modern units. If you have avoided turbine ventilators because of noise, you are making a purchasing decision based on hardware that is no longer being sold. The second weakness was a phenomenon called short-circuiting. This occurred when a turbine ventilator and a ridge vent were installed simultaneously on the same roof. Because the turbine pulled air more aggressively than a passive static vent, it could reverse the airflow through the ridge vent, drawing outside air inward, along with rain, snow, and humidity, instead of exhausting warm air out. The industry response at the time was simply to tell installers to choose one system and commit to it. And because ridge vents were passive, simple, and required no moving parts, the turbine was consistently the one that got eliminated. The modern solution is not a hardware fix, but a systems understanding that was largely absent from installation guidance in earlier decades. Properly designed attic ventilation treats intake and exhaust as a balanced system. Soffit vents at the eaves provide the intake path. The turbine at the ridge provides the exhaust. When the system is designed correctly from the start, with matched intake and exhaust areas and no competing exhaust points, short-circuiting does not occur. The problem was never the turbine. It was installing the turbine without understanding the system it needed to work within. The third weakness was material degradation. Original turbine ventilators were manufactured from galvanized steel that corroded when exposed to coastal air, industrial pollution, and the thermal cycling of repeated freeze and thaw. Corroded bearings seized, corroded vanes warped. Warped vanes created noise and reduced airflow efficiency simultaneously. Contemporary units are manufactured from marine-grade aluminum alloys or stainless steel, materials specifically selected for resistance to corrosion in the most demanding climates. The same unit that would have required replacement within 5 to 10 years in a coastal environment now carries lifetime transferable warranties from major manufacturers. That is not a marketing claim. That is a structural shift in the materials engineering behind the product. The hardware that earned the original's poor reputation is no longer the hardware being installed. So what does this mean in practical terms for a homeowner today? The core value proposition of the turbine ventilator has not changed. It remains a zero electricity device that uses wind energy and thermal buoyancy to continuously exhaust hot air from the highest point of the building. A standard 14-inch unit moves between 350 and 500 cubic feet of air per minute at just 5 miles per hour of wind. It costs nothing to operate. It produces no carbon emissions. And in a hot climate, it works every single day from the moment temperatures begin climbing in spring until they drop in autumn without any intervention required. The energy math remains exactly as compelling as it was in the original data. The United States Department of Energy estimates that attic temperatures in an unventilated or poorly ventilated home regularly exceed 150 degrees Fahrenheit during summer. That heat radiates downward through the ceiling and forces AIR conditioning systems to run longer cycles just to maintain the same indoor temperature. In homes where ductwork runs through the attic, and in many American homes it does, cooled air is already warming back up before it reaches the living space it was sent to cool. Every minute that air conditioning runs to compensate for attic heat that could have been exhausted passively is a minute you are paying for electricity you did not need to use. Proper attic ventilation directly reduces the thermal load the air conditioning system has to overcome. In southern climates, studies have consistently shown energy bill reductions in the range of 10 to 15% from attic ventilation improvements alone. For a standard 1,500 square foot attic, 2 14-inch turbine units are generally sufficient. At current material prices, that represents a total hardware investment of between $40 and $200. Professional installation adds between $100 and $300 per unit, depending on roof pitch and complexity. In a hot climate, the energy savings at even the conservative end of the documented range pay back that full installation cost within 3 to 5 years. After that, every dollar saved is pure gain year after year from a device with no operating costs and no maintenance requirements. No subscription, no service call, no utility bill line item, nothing. There is an additional financial benefit that rarely appears in the energy savings conversation. Chronic attic overheating accelerates the degradation of roofing shingles from the underside. It also creates conditions where moisture accumulates and attacks the roof deck structure. Proper attic ventilation measurably extends the functional lifespan of a roof by preventing both of these failure mechanisms. Given that roof replacement costs typically range from $8,000 to $20,000 for a standard residential home, even a modest extension in roof lifespan represents a financial return that dwarfs the cost of the ventilation hardware itself. You are not just buying lower electricity bills. You are buying years of additional life from one of the most expensive components of your house. The practical limitations of the turbine ventilator have also been addressed at the product level for climates where wind is inconsistent. Hybrid units now exist that combine the passive wind-driven turbine with a small solar panel that powers a supplementary motor on calm, hot days. When wind is present, the unit operates entirely passively with zero electricity consumption. When wind drops on a still summer afternoon, the solar panel provides just enough power to keep the turbine turning at minimum effective speed. These hybrid units are widely available in Australia, where the turbine ventilator never fell out of mainstream use, and are reaching mainstream distribution in the United States. The Achilles heel of the original design, its dependence on wind, has a documented engineering solution that costs roughly the same as the passive unit alone. On the hottest days of the year, the days when your air conditioning bill is at its peak, you are no longer dependent on whether the wind decides to cooperate. The honest picture of where turbine ventilators fit in the modern context is straightforward. If you are in a hot climate, the Gulf Coast, the American Southwest, the Sun Belt broadly, or anywhere in Australia, a properly sized and properly installed turbine ventilation system remains one of the most cost-effective tools available for reducing your cooling load. The hardware that was once legitimately criticized for noise, corrosion, and unreliability has been comprehensively redesigned. The physics that made it effective in 1910 has not changed, because physics does not change. What has changed is the quality of the device delivering that physics into your attic every day, silently, at zero cost. The turbine ventilator did not disappear because the idea stopped working. It disappeared because a generation of cheap, poorly manufactured units built a reputation the technology did not deserve. That reputation outlasted the problem it was describing by several decades. Meanwhile, the industry quietly fixed every flaw, upgraded every material, and solved every failure mode that had caused the original to earn its bad name. The result is a device that delivers the same zero-energy physics as the original, without the noise, without the corrosion, and without the bearing failures. The question now is not whether the technology works. The data on that has always been clear. The question is whether you are going to keep paying your air conditioning bill as if it is 1995, or whether you are going to put a $40 device on your roof and let physics do the work instead. The upgrade happened. Most people just did not get the memo.